be solving this problem called Christmas party. So there are n children at a Christmas party and each of them has brought a gift. The idea is that everybody will get a gift brought by someone else. In how many ways can the gifts be distributed? So our only input is n and it can be up to 1,000,000, and we have to output the answer modulo 8,000,007. So let's head to the drawing board to understand this problem better. So in our problem we have 4 children and each one of them has brought a gift and will give it to some other child. So we can represent the gift given as a graph. So here we'll have the giver and here the receiver. And we will have 4 children, so each one of them has brought a gift and each one of them will receive a gift. And we are told that some gift giving is not good. For example, one cannot give a gift to himself. This way he will not receive a gift he didn't bring. So this is bad. And a good gift given would be something like this. So 1 would give to 2, 2 would give to 1, 3 would give to 4, and 4 would give to 3. And that's precisely what we want to calculate. We want to calculate the number of gift givings that do not map any child to themselves. So how can we do that? Well, it might be interesting to see what are the tools we usually use and try to apply them here. So the first tool that comes in handy and that one should always think about is whether or not it is easier to calculate the complement of this. And to calculate the complement of this, we first need to know what is the total number of possible gift givings. So since each gift given is just a permutation of 1, 2, 3, 4 into some other permutation, for example, this would give us 2, 1, 4, 3, then the total possible number of gift givens is just n factorial. And to make this clear, so the first child will have a choice of 4 children to whom he can give a present. Then one of these children will not be able to receive a present anymore. So the next child will only have 3 choices and so on up to 1. And that's how we get n factorial. So out of these n factorial gift givings, we have to find the ones that do not map a child to themselves. So this would allow us to write the following equation. So n factorial equals good, the number of gift givings we are looking for, plus bad. And this makes sense because any gift giving can be either good or bad. So since we want to calculate this, maybe it will be easier if we just calculated this. So what is bad equal to? So bad is just a gift giving such that 1 is mapped to themselves, or 2 is mapped to themselves, or 3 is mapped to themselves, and so on. So it is the number of maps or the number of gift givings such that 1 is mapped to 1, or 2 is mapped to 2, or 3 is mapped to 3, and so on up to or n is mapped to n. And I hope this makes sense, because if a gift given is not good, this means that one of the children is mapped to themselves. So this encompasses all the bad gift givings. And this does not seem to make the task any easier. We supposedly cannot calculate this right away, but we are always happy to have an OR in what we are trying to calculate, because this will allow us to use our very powerful tool, which is the inclusion-exclusion principle. And if you're not familiar with this tool, we've used it in so many problems so far. I will link a few of them in the description box, as well as the Wikipedia page for this. So make sure to check it out. And what this allows us to do is to break down a proposition where we have ORs into sums of prepositions. So let's apply this to our current example and see what this will give us. So that in our case will be equal to the number of gift givings, where 1 gives to 1, or 2 gives to 2, or 3 gives to 3, or 4 gives to 4. And we know from the inclusion-exclusion principle that this is equal to the number of ways where 1 gives to 1, plus the number of ways where 2 gives to 2, plus the number of ways where 3 gives to 3, plus the number of ways where 4 gives to 4, minus the number of ways where 1 gives to 1 and 2 gives to 2, minus the number of ways where 1 gives to 1 and 3 gives to 3, minus the number of ways where 1 gives to 1 and 4 gives to 4, minus the number of ways where 2 gives to 2 and 3 gives to 3, minus the number of ways where 2 gives to 2 and 4 gives to 4, minus the number of ways where 3 gives to 3 and 4 gives to 4. So basically here the number of ways where 1 gives to 1 may have already accounted for some ways where 2 give to 2. So basically we counted those twice, and in order to not count twice we have to minus a minus here. And we are not done yet because we have to go through all possible subsets of these combinations. So here we have the singletons like each proposition, then we have the ones with the 2 having a minus sign, then we will have the ones with the 3 having a plus sign, and finally we will have the ones with the 4 having a minus sign. So let's carry on. We will add the number of ways where 1 maps to 1 and 2 maps to 2 and 3 maps to 3, plus the number of ways where 1 maps to 1 and 2 maps to 2 and 4 maps to 4, plus the number of ways where 1 maps to 1 and 3 maps to 3 and 4 maps to 4, and finally plus the number of ways where 2 maps to 2 and 3 maps to 3 and 4 maps to 4. And finally we will have to subtract the number of ways where 1 maps to 1 and 2 maps to 2 and 3 maps to 3 and 4 maps to 4. So as you can see, the inclusion-exclusion principle allowed us to break down this formula that we did not know how to calculate into this. But this is not still simplified, so let's try to make sense of it. So in this first line we have the number of ways where one element is mapped to itself. So what are the number of ways that map 1 to 1? So we have 1, 2, 3, 4, 1, 2, 3, 4. In this case 1 will be mapped to 1, and for the remaining numbers anything can happen. We don't actually care at all. We just want to count the number of ways where 1 maps to 1. So basically we can rearrange the other numbers as we wish. And how many ways are there to do that? 3 factorial, because we have 3 elements. So we will have 3 factorial gift givings such that 1 gives to 1. And the same thing will happen for 2. If we fix 2 and 2, then the 3 remaining numbers can be mapped to anything. So we have 3 factorial choices for this as well, and 3 factorial choices for this, and 3 factorial choices for this. What about this second line? In this second line we are fixing 2 elements and anything can happen to the other elements. So here we are fixing 1 and 2. So for example we say that 1 maps to 1 and 2 maps to 2 and anything can happen to 3 and 4. So here we can permute 3 and 4, and there are 2 factorial ways to do that. So this will be actually equal to 2 factorial, and so will this, and so will this, and so will this, and so on. What about this third line? In this third line we are fixing 3 elements, and basically by definition the third element is fixed as well. We only have one possibility. So we have 1 factorial for this, 1 factorial for this, 1 factorial for this, and 1 factorial for this. And finally, what is the number of gift givings where all 4 elements are fixed and there is precisely one such gift giving? So this is equal to 1. So we can notice something here. All the values in each row are equal. So the first row is equal to 3 factorial. The second row is equal to 2 factorial. The third row is equal to 1 factorial. And the final row is equal to 0 factorial. But the number of elements in each row is not equal. For example, here we have 4 elements, whereas here we have 1, 2, 3, 4, 5, 6 elements. Here we have 4 elements as well, and here we just have 1 element. So, is there a way to predict the number of elements in each row? And to answer that, let's see what each row represents. So here we are fixing 1 element. And how many 1 elements can we fix? Basically, we're gonna choose from 4 elements, we're gonna choose 1 element to fix. And to do that, we have 4 choices, and that's why there are 4 elements in this first row. In the second row, we are fixing 2 elements. So it is similar to choosing 2 elements from 4 elements. And that would be equal to 6. That's why we have 6 elements in this second row. And the same goes for the third row. So we are choosing 3 elements from 4 elements. This is equal to 4. And in the final row, we are choosing 4 elements from 4 elements. So this is just equal to 1. So this will allow us to rewrite our formula as the following. So as we said, in the first row we have 4 choose 1 elements. So we will have 4 choose 1 times the value here, which is 3 factorial. And for the second row we have a minus sign, and we have 4 choose 2 elements, and each one of them contributes with 2 factorial. In the third row we have a plus sign, and we have 4 choose 3 elements, and each one of them contributes with 1 factorial. And finally, for the last row, we have a minus sign, and we have 4 choose 4 elements, and each one of them contributes 0 factorial, which is just 1. And in general, we can write that bad for some value n will be equal to sigma from I equals 1 up to n of n choose I times n minus I factorial times negative 1 raised to the I plus 1. And this negative 1 raised to the I plus 1 is just to adjust for the sign. So if I is odd, I plus 1 will be even, and negative 1 to some even power is 1, so it will be positive like for 1 and 3. And if I is even, then I plus 1 will be odd, and this will contribute a negative 1. So now we can use this to actually compute the value for good. So we said that good was equal to n factorial, good of n was equal to n factorial minus bad of n. And we just found out that bad of n was just sigma from I equals 1 up to n of n choose I times n minus I factorial times negative 1 raised to the I plus 1. And just to keep things neat, we can introduce this n factorial into this. So we can represent this n factorial as being n choose 0, which is just 1, times n minus 0 factorial. And since we can write it like this, we can just incorporate it into sigma and start I from 0. And since sigma now is multiplied by negative 1, we can just change this I from I plus 1 to just I. So now the even powers are positive and the odd ones are negative. So this will be just equal to sigma from I equals 0 up to n of n choose I times n minus I factorial times negative 1 raised to the I. So for example, if I is 0, here we will get n choose 0, which is just 1, n factorial, negative 1 raised to the 0 will be just negative, will be 1. So that's how we get n factorial. So great, we found our formula for the number of good gift givings. So we could pre-compute the factorials up to 1,000,000, and we could calculate the binomial coefficient using the modular inverse and modular exponentiation in a reasonably fast time, and we can go through this whole range in O of n. So that looks like we've got ourselves a nice solution, but we could actually make it even nicer with the following algebra. So if we want to simplify our problem further, we will have to look at this. So let's try to see what n choose I times n minus I factorial simplifies to. So what is n choose I equal to? It is equal to n factorial over I factorial times n minus I factorial times n minus I factorial. So this can simplify, and this becomes simply equal to n factorial divided by I factorial. So we can simplify our formula for good of n even further. So this becomes equal to sigma from I equals 0 up to n of n factorial over I factorial times negative 1 raised to the I. So with this, we can calculate our answer even faster without having to calculate the binomial coefficients, and we would need to find only one modular inverse in this case. But we can actually go even further if we notice the following. So to simplify the formula for good of n even further, we might want to find the recurrence relation that involves it. And to do that, we have to bring out an n minus 1 or an n minus 2 or something in this side. So we could do the following first. So we have sigma from I equals 0 up to n of n times n minus 1 factorial divided by I times negative 1 raised to the I. So we know that n factorial is just n times n minus 1 factorial. So this is what we would actually have in good of n minus 1. But the sigma here does not match, because in that case we would only have up to n minus 1 here instead of n. So what we can do is break down this sigma. So this becomes sigma from I equals 0 up to n minus 1 of n times n minus 1 factorial over I times negative 1 raised to the I plus, and then we will just evaluate this when I is equal to n. So if I is equal to n, we will get n times n minus 1 factorial divided by n factorial. I'm sorry, I should have an I factorial here. Times negative 1 raised to the n. And this will simplify even further, so I can bring an n out here. So this is n times sigma from I equals 0 up to n minus 1 of n minus 1 of n minus 1 factorial over I factorial times negative 1 raised to the I plus n times n minus 1 factorial is just n factorial divided by n factorial, so this is just 1. And then this will be just multiplied by negative 1 raised to the n, which will give us at the end. So this is good of n minus 1, so this will be just n times good of n minus 1 plus negative 1 raised to the n. So this is our formula. Good of n will be just equal to n times good of n minus 1 plus negative 1 raised to the n. And we need a base case in order to calculate this. So if we just have n equals 1, so we have 1 here and 1 here, and the only possible mapping is not good. So good of 1 will be equal to 0. What about for 2? So we have 1, 2, 1, 2. We have two possible mappings here, either this or this. So only this one is valid. So good of 2 is equal to 1. And we can see from the formula here, if we plug 2 here, we'll get 2 is equal to 2 times 0 plus negative 1 raised to the second power, which will give us 1. And for 3, we'll get 3 times 1 plus negative 1. So 3 times 1 is 3 plus negative 1 will give us 2. And for 4, we will have 4 times 2, which is 8, plus negative 1 raised to the fourth, which is 1, for a total of 9. So that's pretty much it. This is our formula, and our complexity is O of n. And let's go ahead and check out our code now. So before moving on to the code, I wanted you to know about derangement, and that's the actual name of what we just calculated. So in combinatorial mathematics, a derangement is a permutation of the elements of a set such that no element appears in its original position. In other words, a derangement is a permutation that has no fixed points. So this is our program. We will start by reading n. Then we will declare a vector of long that we will call the derangements of. And we have to go up to n plus 1 because it's 0 index and we have to include n. Then we will mention our base case, which is when n is equal to 1, then the number of derangements is just 0. Then we will just calculate the answer recursively, so the derangements for I would be equal to I times the derangements of I minus 1 plus negative 1 or 1, whether I is odd or even. And at the end we will just print the derangements of n. So that's pretty much it. Let's go ahead and submit. So that worked. Thank you very much for watching. See you in the next video. Bye bye.